Okay, welcome back, students. Let's jump into chapter 4, section 4.1. Okay, so 4.1 is Introduction to Vectors. This is just a brief introduction of some of the properties of vectors. Properties of vectors. One, vector u is equal to the first element of u1, second element u2, dot to un. Okay. Now in this course, typically you would see vectors written like this. Okay, in this course, in this book, we don't write vectors as with the it's like a less than and greater than symbol. I don't know exactly what the symbols are called, but those brackets, we don't write the vectors like that. We just use parentheses to designate a vector, and there'll be a list of values, and that will designate a vector. Okay, we don't necessarily use these symbols to designate vector, although it's commonplace in other courses to use those symbols. Okay, less than, greater than symbols as braces or brackets, to use as vector notation. Okay, but we're not going to use that. Right. Okay, number 2. Okay, vector u plus vector v is defined by the parallelogram law geometrically and if u is a two-dimensional vector, u1, u2, and v is also a two-dimensional vector, v1, v2, then u plus v is equal to u1 plus v1, comma, u2 plus v2. Okay, number 3. Vector u plus vector v is the same as vector v plus vector u. Okay, so vector addition is commutative. Number 4. Vector u plus vector v plus vector w is the same as doing vector u plus v first and adding w. So it's associative. Okay, it's additive associative. Okay, number 5. Okay, u, oops, not mu, sorry, u plus the 0 vector. This is just a vector in whatever space that we're working in. whatever vector space we're working in, you know, whether it's 2 space, 3 space, 4 space, whatever, whatever, however many dimensions it has, that zero vector is just all zeros. Okay, for those dimensions. Okay, and this is just equal to u. Okay, and so this has an additive identity. Okay, of the zero vector. Additive identity zero vector is the zero vector, is what it's called, zero vector. Okay, and it's just zeros for however many elements or entries this this vector has. Okay, however many dimensions that vector possesses. Okay, number 6. U, vector u, plus negative vector u is equal to the zero vector. So this is an additive inverse. Okay, negative u would just be equal to negative u1, negative u2. We're just going to negate all of the components of the vector. Okay. That negative un. Okay, number 7. Scalar multiplication defined as R of u1, R times u1, u2, dot, un. Okay, maybe I'll move this down. Here, so it's all one thought. Is equal to R u1, R u2, dot, R un. Okay. Okay, number 8. Okay, 1 times u vector u is equal to vector u. Okay, so scalar multiplication creates a multiplicative identity. Number 9. Scalar s times scalar t times vector u is the same as scalar s times vector t times vector u. So once again, there's a multiplicative associative nature of the scalars. We haven't talked about how to multiply vectors yet. There's a couple different ways to do that, but where have we? I don't think we have. No. Okay, and so you have s times t and then u is equal to s times t, yeah, exactly. Where s and t are scalars. Okay. Number 10. Okay, R times U plus V. These are two vectors. Scalar R times two vectors being added together. Okay, is equal to R times U plus R times V. Okay, where R is a scalar. Okay, and number 11, S plus T times vector U, okay, is equal to S times vector U plus T times vector U. These are kind of like distributive properties in a way. But again, we can only distribute the scalars over the vectors. Okay. We're not doing anything to distribute two vectors together. Okay, so this is really limited to just scalars behaving and their behavior over a vector or two vectors, but not two vectors together. Okay, S and T are scalars. Okay, let's do a simple example here. Okay, let vector x equal 2, 3, 0, -4, and vector z equal 5, -3, 2, and -2. Okay, find vector y, an element of R4, such that 2x, 2 times the vector x plus -3 times the vector y is equal to negative vector z. Okay. Okay, so let's see what we can do here. Okay, so 2 times vector x. Well, that's 2, 3, 0, and -4. Plus -3 times vector y. Is equal to the negation of z. That's just -1 times. We're just going to negate every single one of the values in there. So maybe just write the opposites. Okay, -5, 3, 2, -2, and 2. Okay, negative z. Okay, so now distribute the 2 to every value in x, vector x. We get 4, 6, 0, and -8. Okay, plus -3 times vector y is equal to -5, 3, -2, and 2. Okay. So now what can we do? Well, I can add the opposite of this vector to both sides. Okay, and what I will get is I'll get 4, 6, 0, -8 plus -4, -6, -0, which is just 0, and -8. Okay, plus -3y equals -5, 3, -2, 2, plus my negation of 2x. And so that's going to be -4, -6, 0, and -8. Okay, if I add it to one side, I have to add it to the other. Okay, what will happen if I add these two vectors together? I will get the 0 vector, okay, in 4 space. Okay, so 0 vector plus negative 3y is equal to, add components to each other. That's going to be negative 9. That's going to be negative 3. That's going to be negative 2 and negative 2 and negative 10, right? No, we've got negative 6, sorry. Oh, that makes sense. Okay, and now what we want to do is we want to divide, well, the 0 vector and the 0 vector added to another vector, that's just up here at number 5 here. So the 0 vector plus a vector is itself. That's the additive identity. So that's just going to become negative 3 times the vector y, okay, is equal to negative 9, negative 3, negative 2, and negative 6. Okay. So now this becomes, I can actually multiply a vector times a scalar. So if I multiply negative 1/3 times this vector, that's the same as negative 1/3 times negative 3 times the vector itself. Okay, I could reassociate those two. Okay, and so that just becomes 1 times vector y. If I do it to one side, I have to do it to the other side. I'm going to multiply that vector, resultant vector here, the resulting, sorry, not resultant, the resulting vector here, negative 1/3 times that. So we're just going to end up dividing everything through by negative 3. And so we will get 3, 1, 2/3, and positive 2. Okay, now that will give me 1 times vector y. Well, that's just the multiplicative identity. 1 times vector y is just vector y, because this 3, 1, 2/3, and 2. And so we get 3, 1, 2/3, and 2. Okay, using those properties of vectors, that was 11 properties of vectors from above. Okay, let's do another example here. Example number 2. Okay, let vector v be an element of R3. Okay. And RS, okay, this is 3 space. This is yeah, R3 is just 3 space. It's just 3-dimensional space. Okay, 3 coordinates. Okay, R and S, they're each elements of just the real number system. They're just elements of R1 basically, which is just R. Okay, one-dimensional numerical values. They show that RS times vector V is equal to R times S times vector V. Okay, so let's just get a generic V in R3. So V, we could say, is V1, V2, V3. Okay, now we want to say that we have RS times vector V Okay. Let's just do vector v here. The RS is equal to RS times V1, V2, V3, okay, which is going to be equal to, distribute each of these, okay, RS V1, RS V2, RS V3, okay. And I can kind of group these together now that they're inside. And I could say, well, R is being multiplied by each of these, so I could essentially say that R was on the outside of those. And so R, we're kind of factor out the R. And so we get R times SV1, okay, SV2, SV3. Okay. And then we could do the same kind of with S and factor that out. And we would say that R times S times V1, V2, V3. Okay, but V1, V2, V3 is equal to V, vector V. So this really is R times S times V, vector V, and so we have shown that they are equivalent, and so we can just put a little square there, saying we're done. Okay, we're done with that. Okay, we have shown that those to be equivalent statements. Okay, that's an introduction to vectors 4.1, and I'll see you in the next video for 4.2.